Well, good morning. This is Thursday morning, the 18th of June, 2020. It's 8:34. I've been here in the Zoom meeting waiting for someone to show up since 8 o'clock. 8:30. And so far, nobody's gotten here. I went back to Blackboard to make sure I had posted it. It was posted. Everything is correct. I don't know what the problem is. I don't know if there's some difficulty with wireless somewhere or something, but not a single student is here yet. So rather than waste precious time, what I'll do is go and start with class, since I'm recording everything right now, and start with the class and continue, and hopefully I'll see you when you're trying to come in. So don't know where everybody is, but let's go from there. So the first thing I'm going to do is enter full screen, I think, and then I will start a screen share first with the book that Billy sent me. Okay, and I will also, okay. Well, this is where I had planned to begin, but let me first move this taskbar as much out of the way as I can. Okay. All right. Now, I see, oh, here comes the student, thank goodness. Can't see who it is yet because it blacked it out. Melissa's here. Thank you. Okay. All right. Melissa, can you hear me yet? Still logging in?
Hello.
Okay. I was afraid maybe I had done something wrong and not sent the Zoom invite correctly. I've been gone out and checked Blackboard to make sure it went and all that kind of stuff. I'm so glad to see you because I was afraid something was wrong. Okay, but glad you're here. Okay, any questions, issues, concerns?
No,
I'm sorry, I can't hear.
no, sir.
Okay, great. Well, where we're due to start today was on Chapter 2, First Order Differential Equations, Section 2.3, Linear Equations. And we talked about the error function last time, and we didn't have time to do anything with it. So this is just a quick review of what the error function is, how it looks. Here's the error function here. And you can see my book, right? Okay, good. And there's the complementary error function. And if you notice, this one goes from 0 to x. This goes from x to infinity. So basically, the two of these have basically the probability that everything could happen that could happen between 0 and 1, and that's a probability of 1. So the sum of those has to equal 1. So the error function is going to be a number less than 1. The complement less than or equal to 1. The complementary error function is going to be a number less than or equal to 1, but they've got to add to be 1. Okay, so that's what we talked about briefly last time, and I think we blah 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 some more here. Here is the problem example with the error function. Okay, solve this initial value problem. Now I don't know if you can detect if anyone else is trying to get in or not. I have this box. I don't know. Can you see the box that's now fading out at the bottom of the page? It's a rectangle.
Yes, sir.
Okay. And when you see it come back, you see it's black in the middle and says, please move this window away from the shared application.
Yes, sir.
You can see that. Okay. But when someone comes into the room, can you see their name under that? That's what happens. It blacks them out, so I can't see them either, but usually I'll see some writing underneath this that's trying to admit somebody. If you get a sense that someone's trying to come in, please stop me, because I'll get focused on what we're doing and might miss them. Okay, so let's move on. Let's solve this differential equation. So, want me to go to the whiteboard? That's where we usually go.
Yes, please.
Okay, so let's go to the whiteboard. And okay, now I've got to get this taskbar out of the way. They put the taskbars just, well, not as inconveniently as possible, but they seem to do a good job of getting them there. And then let me move the whiteboard so I have as much white writing space as possible. Okay, that's about it. Okay, here's your initial value problem. dy dx is a differential equation. And this box keeps coming and going. I get so paranoid I'm missing someone. I get distracted by it. I wish it would only show up when someone is coming in, and then it would get my attention. But it just keeps doing, and then I start ignoring it, and there I miss someone coming in. Minus 2xy okay, is equal to 2. Okay, with the initial condition that y of 0 is equal to 1, I believe it is. Okay, yeah, there's our problem. dy dx minus 2xy is equal to 2. Okay. Now, frankly, no, it can't. I was just going to say this could be solved by separation of variables. It could if that were a 0 there for the 2. That's not a 0, it is a 2, so that was going to preclude our being able to use separation of variables. I always check that because it's easier to do. But this is set up perfectly for a linear equation. Your coefficient of your derivative is 1. That's what we want. The coefficient for your y is a function of x alone. That's what we want. That's our p of x, by the way. And over here, our f of x, or whatever they are calling it now, that's also a function of x, which is a constant function of 2 with an initial condition. So we're ready to roll. What's the first thing we do? Basically, I've already done it. Identify your p of x. What is it? Minus 2x. Don't leave off the sign, okay? It's a minus 2x. What do we do with that? We integrate it. So I'm going to just integrate the variable part, get the minus 2 on the outside, minus 2x. I mean, minus 2 times the interval of x dx. And I think we probably should have left the minus in there. What does that integrate to become? And again, we never put a plus c with this one. What is that going to be? The minus sign is still going to be there. Antiderivative of x is x squared over 2. And that wipes out the 2, so that just gives you minus x squared. Now what do we do with that one? The integral of p of x dx, you e it, okay? So you raise that to the eth power, okay? That is your integrating factor, e to the minus x squared. So what do we do with it? We multiply it by each term on both sides of your equation. So it becomes, this is the tedious part, e to the minus x squared dy dx okay, this is so tedious, minus 2x e to the minus x squared y, why not, is equal to 2 e to the minus x squared. Now, that's ugly too. All right. Why did we do all this? Because this is supposed to produce a perfect derivative on the right-hand side, left-hand side. And this is supposed to be d by dx, whatever your independent variable is in the bottom here, of your integrating factor, e to the minus x squared, times y. That is supposed to be what the result of doing all this magic up here did for us. Let's see if it did. If what they claim, what it was supposed to do, that is an x. That looks more like a y, doesn't it? Okay. All right. Let's see if it does. D by dx, like saying that, of this thing, product function, would be in the first, e to the minus x squared times the root of the second, dy dx. That part's perfect. And supposedly plus the second, y, there it is, times the root of this. So what is the derivative of that? It's e to the minus x squared. That's okay. Then chain rule times a minus 2x, and sure enough, there's your minus 2x. So that is a perfect derivative of a product, okay? And this is equal to 2e to the minus x squared. And that is a 2 there. That's an ugly 2. See if I can make this one a little better. A little better. Okay. So what do we do with that? Well, we write this in differential form. And, yeah, let's do that first. This is d of e to the minus x squared. That's why I don't like arrow functions. There's so much to write in them. And there's more yet to come. Okay. There's your product function is equal to 2 e to the minus x squared dx. All I did was write the previous line in differential form. To the top part here on this side and whatever we had over here times your dx on this side. Okay? Writing that derivative in the previous line as a differential in the bottom. So now we we integrate both sides. And the integral of a perfect derivative by fundamental theorem of calculus, which part? Part 2 maybe, or second fundamental theorem of calculus, whichever. One of those, okay? You integrate both sides, and the left-hand side, by that, just gives you the argument here, because the integral undoes the perfect derivative, okay? So you get an e to the minus x squared times y that part was easy, is equal to, now here comes the rub, 2 times this integral that is impossible to integrate. Absolutely impossible to integrate. It's a non-elementary function. There is no way you can integrate that. Okay. The integral of e to the minus x squared dx. But let's pause for a moment here, go back to our book, and we've still only got one person here, Melissa. Thank you for being here. I hate talking to myself. That's not a very receptive audience. Okay, let's go back here to the error function. And of course, Melissa, you're in the way. You realize that? You can't see this, but your block is right there where I need the button to move the button. So here it goes. Actually, the arrow is better. The button moves too much. So let's see. Let's go back to this good old arrow function thing here. All right, here we have it. Let me get it in this form. Here we go. This is basically what we've got there. The integral, and we don't have limits on it, but the integral of e to the minus t dt, e to the minus x squared dx, same deal, okay? And we don't have any limits on it, so that makes this a little awkward, but we know this integral here, just put x's in the place and leave off the limits here, is equal to the square root of pi over 2 times the error function. That's all we have to put, except we already got a 2 in front. So it's just square root of pi times the error function, because remember we have that 2 in front of our integral. So let's go back. It's square root of pi times the error function. You don't have to try to solve anything with it. You just write that down. Okay, here we go. Here's what we have there. This part here is 2 over root pi. So this part here is root pi times the error function. So this is equal to root pi times the error function. Let me make sure I'm writing it the way they do. Well, actually, they leave it in integral form and do their they go on and put the limits on. So let's go back and do that. Now we have this box in the way, and I don't know for sure why it's there, but it's there. So let me erase this. I jumped the gun a little bit on this part. What they want to do is make this look more like the error function. Like I said, we don't have limits here, but since our initial value is y of 0 is equal to 1, we can write this as and I think this is what they do. Well, they choose a strange way to go about doing it. All right. Okay, up to this point, we're in complete agreement. d by dx of e to the minus x squared y is equal to 2 to the minus x squared. Yeah, e to the minus x squared. Okay. So at that point, and let me go on and erase the bottom line down here too. They don't get here yet. They're going to get here, but let's get it the same way the book does. We could have gone the other way. Okay, so what they do here, at this point, they put limits in. And they put a limit of 0 on the bottom and x on the top. Now, as soon as they do that, you can't put an x in the in here. So this has to become a t. Okay. Okay. So this becomes a t. And knowing that, this also is going to become a t, and that's going to become a t. Okay. Now, they do one other thing that is okay. I mean, it's correct. They rewrite this as d by dt, and then they put a dt here as well. And that's fine too, because dt over dt is 1. And they put the same limits here, 0 to x, because that's what we're going to, finding the function of x, and put the t here and the t here. All right. Now, that's all a legal thing to do. I didn't finish this, did I? D by dt. I just put a d by d. Okay. A dt here, dt there. That works. Okay. Now, oops. Left off my t in here too. I erased the x, but forgot to put the t in. Okay. So now we've got it pretty much looking like they did in the book. Okay. Now, this side here is still an integral of a perfect derivative. It's just that you have limits on it now. So what you do is, this is your argument. This is what's going to come out of it. And you evaluate that first when t is equal to x. And then you evaluate it, subtract off when t is equal to 0. Okay? So that's what we're going to do next. That will be evaluating this integral. This is an integral of a perfect derivative. So it's just this argument evaluated between these two limits. So that's e to the minus x squared times y of x, which, by the way, is what we're looking for. What is y as a function of x? That's what we're doing in our differential equation up here. That's what we're looking for. But it's minus e to the 0, well, that's 1, okay, times y of 0. Y evaluated when x is equal to 0. Well, guess what, team? We know what that is as well. That's 1. So I'll put that in the next step, but I wanted to write it out here for you. Okay? And that's equal to 2 times the integral from 0 to x. And I don't know why they didn't go on and evaluate this one, but they didn't. E to the minus t squared dt. Okay. Now, what this is like we said before, this is pi, no, square root of pi. That's supposed to be a square root sign. And that's supposed to be a pi. Pretty ugly. The square root of pi times the error function of x. Okay. Now, that's what this thing is from what we looked at before. Okay? Now, I don't know why they carry it around and carry it around and carry it around, but they do. Okay? It's just so much easier for me to write that as root pi times the error function. Okay. Now, let's go to the top up here. Now, one thing that we'll note. Well, let's go on and do it. This is equal to 1. So I'm going to wipe out my y of 0 now and just put 1, minus 1. Okay? Minus sign from there, 1 there. Okay? Now, I think what I'm going to do, if it's okay with you, I'm going to do 2 steps at once. Okay? Oh, here comes Cole, I believe it is. I believe I caught his name or before it blacked it out. Cole's here. So the bottom part of the alphabet is doing their job here. They came. They showed up. Where is the top part? And the middle part. Okay. So it's unbelievable. It's strange how classes go. Of course, this is a really small class. This whole class is in the top part of the alphabet, basically. We got 2 B's, a D, an E, an H, and an M. Okay, only 1 M. Okay, and that's Cole. In some of my other classes, they're almost exactly the reverse of that. Like this evening's class, the next morning class is 1 in a D, and then the rest of them are in the bottom part of the alphabet. So it's rather bizarre. And I have one class, if I can find it, almost the majority of the class are W's. I mean, it's just really, that's completely irrelevant to anything. I just find those kinds of things really strange. But welcome, Colt. Glad you're here. We're doing example 7 on page 61, chapter 2, first order differential equations, 2.3 linear equations. And we had talked about the error function last time, and it really is hard to write. I'm trying to skip as many steps as I can. So here's what we got. You'll have to go back and see how we got this. E to the minus x squared times y of x. This is what we're looking for, y of x. Keep hold of that idea. Minus 1, because it's an initial value problem that y of 0 is 1, is equal to 2 times this strange-looking function here, which is related to the error function by 2 over pi. 2 over root pi times this thing is the error function. So I multiply the error function by root pi, and you've got what this thing is. I don't want to write that integral anymore, so I'm just writing it as root pi times the error function. Okay, here's what I'm going to do next. Since we don't want to isolate the y of x, I'm going to do 2 things at once. I'm going to add 1 to this side. So this is either going to be root pi error function of x plus 1 or 1 plus root pi error function of x. I don't care which way you write it, okay? So that's the first thing I'm going to do, add 1 to both sides. And then the second thing I'm going to do is multiply everything on both sides by e to the x squared. Because that will wipe this one out, because e to the x squared times e to the minus x squared. Keep the base, add the exponents, that's e to the 0, that's 1. Okay, so I'll multiply the 1 by e to the x squared and multiply this too. So here's what we get. Here is our answer. Y of x get it right, is equal to, now I think I'll start with the plus 1 that I did there, but then I multiplied it by e to the x squared. Well, the e to the x squared is multiplied by everything on this side, so let's just pull it out. E to the x squared, it's pretty ugly writing, okay, times 1 plus root pi times the error function of x. And you might say, what in the world is that? And I'd say, look it up. No, I mean, what you do for any value x, I probably should have put a bracket there, but I'll put double parentheses. For any value x, you're wondering what the solution for this thing is. Go to a table that gives you the error functions. Now remember, it's always something between 0 and 1. It could be 0, it could be 1. Something between 0 and 1. Multiply it by root pi, which is something on the order of, what is it, 1.7 or something like that, square root of pi, I don't know. And so add that to 1, so you get something on the order of 2 plus 7 or 6 or 7, something like that. And anyway, plug in an x for your error function that you looked up in the table, multiply that by root pi, add 1 to it, and then multiply that by e to the whatever x value you're looking for squared. Okay, that's it. That gives you your function. Not something you can derive analytically. This is as far as you can go analytically. You have to use a table. Or, of course, this is all online somewhere. You can go to error function online and get all the values you want with the error function. So whatever x you're interested in evaluating this or finding out what it would do for you, that's what you do. Now let's see if that's the answer they get. Yeah, y is equal to e to the x squared times, and they put a bracket there, which I should have, 1 plus root pi error function of x. That's it. Okay. Now, they show the graph of this. Oh, I was going to show you in my book. We don't have to do that anymore since Billy sent me the book, PDF version of the book. So let's scoot down and see that again. There's our problem, there's their solution, and there is their answer. So the graph of this, obtained with the aid of CAS, this computer algebra system, I think is what they're called, is given here. There is that. The initial value is right there. It's a negative over here and positive over there. Okay? You might say, well, wait a minute, I thought error function is always something between 0 and 1. And it is, okay? But, well, that's hard to explain. Yeah. E to the minus x, okay? I mean, e to a very small number is going, well, that's still, I don't know. I can't, I don't know if anything on the negative side is even valid, but this is what it looks like. When will you ever use it? I don't know. I don't know what your major is. I don't know what you'll be doing with it. If you ever need the error function and you manipulate it like this, it will produce an answer. And because, well, we just can't speculate. Here is a driver of this. This is what's driving it. The error function is not really driving it, it's contributing to it. And you can legitimately put a negative x in here, but that throws everything into sort of wackiness, and that's where you get the negative values here. And I don't know what application you would use it in, but I have a feeling you wouldn't be using the values down here. Possibly the ones up here. All right. Now, I think I beat that horse to death. Let's move on to use of computers. And they mention Mathematica and Maple, and they're capable of producing implicit and explicit solutions for different kinds of equations. And they go into this. I don't have it, so I can't do anything with it. If you have access to it back at your home campus, by all means use it. You know, it's pretty powerful stuff. Okay. remarks that are here. Usually I avoid these as much as possible. First time I taught the course, I thought it was important to go through them in gory detail, and it'll bog you down like crazy. And it says, occasionally a first-order differential equation is not linear in one variable, but is linear in the other variable. Okay. This one would be the case of that. It's certainly not linear in y. But if you rewrote this as dx dy, you flip this side to x plus y squared. You could bring your x over here, leave your y squared out there. Yep, there it is. You now have a linear equation in x, not in y. And that's a legal thing to do, and you can solve this. The question is, once you get it solved, can you go back and get it as a function of y alone? More than likely not. This does come up with a solution. We're not doing it. X as a function of y. Try getting this back into a form of y as a function of x. Not going to happen. Okay? So that's an implicit solution, they say, of the first equation. This is an explicit solution of the second equation. Okay? Now, they like to give names to it. The word transient we used before. One of those input and output functions pop up, especially when you're dealing with things like statistics and probably industrial engineering. I don't know that for sure, but I'm guessing that might be. The input or the driving function and the output or the response function. Okay. There are some other special functions similar to the arrow function. One of these is the sine integral function, and then there's a related Fresnel sine integral function. Now, we're not going to do those in this course. They do at least mention them. I think there's going to be more on the next page, but we'll see. Potential paper topics. How do you use these things? Any one of them. The arrow function, the complementary arrow function, examples of driving functions, output, input, response functions. Who uses that? How? Those would be good paper topics. Sine integral function. Who in the world uses that? What's it used for? What kind of applications? Who in the world is Fresnel anyway? That would be a paper topic. And how is his sine integral function different or refines or whatever the other? Nope, they don't give anything about that. I think it'll show up later. It says in problems 47 and 48. So, if you want to go there, you certainly can. Homework exercises here. Any of the odds, 1 through 23, okay? If they're in the back of the book, they are legitimate. Okay, just make sure no one else has tried to come in. No, still got it. I just don't see Melissa's name anymore. I see Cole's. I wondered if she had to X out for a minute, but she's still here, so good. Okay. Any of the odds 1 to 23 that are in the back of the book, these should all be doable. You certainly don't have to do them all, but give them a shot. Some of these you have to work on to get them into standard form, like that one's, well, that's even. Here they change the notation on you. That doesn't change anything. Here you have to divide by x squared. Here you divide by x. Yeah, you see various things you have to do. They put primes here that you still have to fiddle with. Here they wrote it in differential form. You have to write it in derivative form. Now here's somebody else trying to get in. I can't see who it is. I'm guessing it's Corbin. Could y'all see the name? That looked like a C to me. So I'm guessing that was Corbin. Yeah, that was Corbin. All right. So welcome, Corbin. We now have half the class here. Okay. About half the time is gone, but I'm glad y'all are here. Okay. So, any of the odds, we're talking about the homework exercises in 2.3. Any of the odds 1 to 23. that you want to do. You certainly don't have to do them all, but make sure you feel confident about those kind of problems. Okay, then any of the odds 25 to 35, let's see if I can get all those on the page. There they are. Those are initial value problems. You should be able to handle those pretty well. And then you got 37 or 39 down here. Those are similar to example 6. Okay, 37 or 39. Then you should be able to do 41. Another proceed as example 6. That's a piecewise defined function. 43, if that answer's in the back of the book, that's a legitimate homework problem. So give that a shot. 45, another one, initial value problem. Now we see the sine integral function. I knew it showed up somewhere here. Let me see if I can get it so you can see the whole thing. There we go. There is your sine integral function. You can fiddle with that if you want to. They give you what it is. Then they give you a differential equation. I'm almost guaranteed it's going to use it. Okay? Similar to what we did in that last example. And then they give you the Fresnel sine integral function. Okay? And they say see Appendix A. I think that means that's where they're derived. If you want to go to that extent, you can. But here's the Fresnel sine integer function. It's not, in fact, it looks fairly different. The limits are the same, 0 to x. Sine's in there, but this is sine t over t. This is sine of pi halves t squared. So they, frankly, to me, don't look anything very much alike. However, maybe in Appendix A they give some of the values of. I don't know. I haven't gone back to check. You don't need to mess with that, certainly 48, except if you want to use that as a paper topic. Okay. The other issue here, everything else is discussion problems. Only if their answers are in the back of the book would I even consider doing much with them. Except, let's take a look. There's an application problem. Well, that's on mathematical models. Radioactive decay, if you're interested in that, by all means go for it. Now, it seems like I remember that Melissa is aren't you a biomedical engineer? If that's the case, you may be interested in the heart pacemaker here. There's a differential equation that you deal with in that. RC circuits, you may not be at all interested in that, but that is at least a health-related application. And there's computer lab assignments. I'm not going to make any of those because I don't have the software. If you do and want to play with it, you certainly can. That's up to you. Okay. Now, if any of those discussion problems do have answers in the back, it may be worth looking at those just to get a good handle of what's going on with those. All right, but I'm not requiring it. So we're moving on to exact equations. And this starts at the bottom of page 64. Any questions on 2-3 before we leave it? All right. If you noticed, one of those homework exercises, at least one of them, I remember at least one, showed up in differential form rather than derivative form. And I said, this one you're probably going to have to get in derivative form to get it in your standard form for a linear equation so you can solve it. In these, we're going to be looking at equations and we're going to use them in differential form. In fact, I think this is the only set that we intentionally do this way. Well, I don't know. Separation of variables, you basically do this too. But here's a simple first order differential equation. Y dx plus x dy is equal to 0. And I basically just gave it away. Hey, there's no reason in the world not to move this term or one of the terms, it doesn't matter which one, to the other side. And then you can separate the variables. So that's both separable and it's also linear. To get linear form, you'd have to get dy dx, so divide both sides by dx in a sense. and you would have x dy dx plus y is equal to 0. Divide by x. There, sure enough, it's a linear form. So it's a separable form. It's also a linear form. So you can solve that equation by another method, and this method happens to rely on a good observation, that if your original function was f of xy, the function of those two variables, both independent variables xy, if you have that equal to x times y, and then you did a total derivative of this, that would be y dx plus x dy. There you have exactly what we have on the left-hand side. And if you set that equal to 0, that means your derivative of this thing is equal to 0, meaning that function has to be a constant function. Okay? And this is sort of wiggling all over the place. In this section, we'll examine something a little more complicated. I'm going to scroll this down just a little bit. So, yeah, it's okay. In this section, we'll examine something a little more complicated. Well, a lot more complicated. And that is equations written in this form. Some m of xy, that's some function of the two independent variables x and y, dx, plus some other function of those independent variables, n of xy, dy, equals 0. Exactly the type of thing we have here. Now, these exact equations, this differential form you have on the left has to be equal to 0 on the right. That's a key, okay? And just like we said here, this thing has to turn out being a constant function, okay? Now, don't get too bent out of shape on that. That becomes your constant of integration, because again, this is a first order differential equation. That's all the things in this chapter are dealing with. You need one parameter, to solve a first order differential equation. That's what gives it to you. Okay, so the question is then, can we come up with a function f of xy such that it's the m of this is the partial of that with respect to y. No, partial of this with respect to x, because if you take the derivative of this, the total derivative of this, that'd be a partial of this thing with respect to x dx and partial of that thing with respect to y dy. So if this is a partial of this with respect to x, and this is the partial of that with respect to y, then you can solve this by partial integration. Okay, let's move on. I know this is behind the box. Okay, so what we're dealing with is the differential of a function of two variables. So they start making all sorts of name changes. They love to do this. Sometimes they use them and sometimes they don't. This time I guess they will. If z is equal to f of xy, okay, that's legitimate. If x and y are both independent variables, you got to have a dependent variable, so let's name it z. Z is a function of x, z is a function of y. Okay, those are independent variables. Well, I shouldn't say it quite that way. Z is a function of both x and y. So a function of two variables with, now here's a catch, with continuous first partial derivatives in some region R. Now I'm trying to remember, I think all of you folks have had Cal 3, haven't you? I'm trying to remember if anyone is taking both of these at the same time. I can't recall. I know Dawson and Ricky have had Cal 3. I'm pretty sure that Melissa, I believe Cole and Corbin have, so I think everybody's had it, but I don't know for sure. Billy, I'm assuming yes, but I don't know that for sure. Am I right on the two of you? Have you all both had Cal 3? Melissa?
No.
You haven't. Okay. So have you taken partial derivatives before?
I have not. I'm actually in Cal 3 right now.
Oh, you are? Okay. Okay.
Yes, sir.
So we're probably ahead of you there. So I will take the time to explain how to do a partial derivative. That's what I was getting at. Okay. So just hang on to the words now. I'll tell you how to do it later. So this z, f of xy, is a function of two variables. And anytime you're taking a derivative, now remember early on we said we're not doing partial differential equations, but I think I coupled that with that doesn't mean we're not taking partial derivatives. It's that we're not solving partial differential equations. Those are two different things there. They certainly have to be a little related, but they're not the same thing. So this function, y is a function of z is a function of x and y, is a function of two variables, two independent variables, x and y, and it has to have continuous first partial derivatives in some region R in the xy plane. Now, if you haven't had this in Cal 3 yet, let me just give you a description. When you're dealing with single variable calculus, y is a function of x. Your domain is the x-axis. Your range is somewhere on the y-axis because you have one independent variable x or t or whatever it is that's usually described on the horizontal axis. And then your function describes what's happening with those inputs on the vertical axis. Okay? Now, since we have two independent variables now, your domain is no longer just the x-axis, it's some region of the xy plane because you have two independent variables, x and y. So you have your domain is a region R of the xy plane. Okay? Now, it doesn't have to be the entire xy plane. This function z is equal to f of xy has to have continuous partial derivatives on a given region of the xy plane. You can't have any going to infinity there or something else. It has to have continuous partial derivatives in that region. Okay. And then it says, then recall from calculus that the differential, I realize now I've been saying these words and you probably didn't know what I was talking about. This is how we define the differential of a single dependent variable, multiple independent variable. And we're going to leave it at two, so just two independent variables. dz, that's how much z, the dependent variable. So if you can now, if you're a visual person, picture your xy plane down here somewhere. That's your domain. Some region of that is your domain. Z, there's your independent variable. Used to be y, now it's z. But y used to depend only on x. Z depends on both x and y independently. So your z up here is going to describe some surface on top of that portion of the xy plane. Okay? So that's what we mean by that. So if you're taking the derivative of z, how is z changing? That's what dz is. How is it changing? Then that would be, now you don't probably know what this is, the partial of f, this function here, with respect to x times your dx, any little thing, plus the partial of y with f with respect to y dy. So let me sort of briefly tell you what that stands for. So f is the function up here, the z, okay? And your domain is down here in the xy plane. Let's just take only changes in x to begin with. So how is f, or z, up here, changing with a small incremental change of x? Well, basically what you do, you set y equal to a constant. You just ignore y. Pretend it's a constant. Whatever constant that is, now the xy plane is down here, x-axis this way, y-axis this way. Pick a constant y, and then look at how f is changing on that curve that cut through your surface up here that was your your z, or your f of xy. And that basically gives you a derivative. That's called the partial derivative of f with respect to x alone. And then multiply that by that incremental change of x. Okay? But then do the same thing. This time pick an x value to be constant and look at what that plane cuts the surface up here and how f changes with y alone. So the partial of f with respect to y would be the derivative of f with all the x's held constant, and you only take the derivative with respect to y. That's what a partial derivative is. Partial derivative of f with respect to x. Even though f is a function of x and y, for the partial of f with respect to x, treat all the y's as if they're constants. If you have numbers in there, they are constants. Just treat the y as if it's a constant, and take the derivative of that function with the numbers and the y's treated as a constant, and only take the derivative with respect to x, multiply that by your increment there, and do the same thing here, only take the derivative of f with respect to y alone, treating the x and all the other constants as constants, and then that's multiplied by your dy. So this is what we mean by the differential of that. Okay. Now, here's the deal, and remember I said this in the beginning. In the special case, and I'm going to scroll down a little bit because that box I think is blocking you from reading. Okay. All right. In the special case where f of xy is a constant, and remember we started with a function, a differential expression, but it was equal to 0. And I said, if this can be represented by a function xy, if its differential is 0, that means that function f of xy is a constant. Okay? So in that special case where that's true, then this equation becomes partial of f with respect to x dx plus partial of f with respect to y dy. If that's a constant z up there, then the derivative of a constant is 0. Now, so therefore, if you have an equation that's written in the form of m of xy dx plus n of xy dy is equal to 0, if that m can be represented by this, and if that n can represent something like this, for the same f, then you can solve this differential equation. This is called an exact differential equation. Any old functions m and n won't work, only if they can, if the m can be this and the n can be that. So in other words, given a one-parameter family of functions, f of xy is equal to c, we can generate a first-order differential equation. Now here we're doing it backwards. They're giving us the function. It's a constant function. You can generate a first-order differential equation by computing the differential on both sides of the equality. So what if this was your function? X squared minus 5xy plus y cubed is equal to some constant. That's your function, okay? Then what we do is take the partial of this function right here, partial of that with respect to x, okay? Now again, what do I mean by that? Treat the y's as a constant. So the derivative of this function with respect to x alone would be 2x. That's where that comes from. And over here, we treat the y as a constant. The minus 5 is already a constant. So basically, this is minus 5y times x. The derivative of that would be minus 5y. The derivative of y cubed, well, if y is treated as a constant, y cubed is a constant. The derivative of a constant is 0. So this gives you your partial of f, this function f right here, times dx. There, you just bring down the dx. Now we do the partial with respect to y. No y's here, so that partial is 0. Here's a y to the first power here, so that's a minus 5x. That's all you have. And over here, plus 3y squared. So minus 5x plus 3y squared, and then multiply that by dy. And because this is a constant, the derivative of a constant is 0. Okay, so now we've created a differential equation that you basically already know the solution to. Okay, here's the solution. Well, that's not quite the solution, but that your f of xy is equal to some constant. See, that this thing right here is equal to a constant. Okay, now, sort of what I've been warning about, they're mentioning here. Of course, not every first order differential equation written in differential form, m of xy dx plus n of xy dy is equal to 0, it doesn't correspond to some function, f of xy is equal to c, because the partial of this with respect to, this may not be the partial of a given function of x, y, f, and this being the partial with respect to y. This has to be the partial of that function with respect to x. That has to be with respect to y. You can make up all kinds of functions. That's not going to be true for. So for our purposes, more important to turn to the foregoing example around, namely if we are given a first order differential equation. That's why I said we're doing this one backwards. Given a first order differential equation, such as this one, that's a first order differential equation. We don't know that it's linear. We don't know that it's separation of variables. I'm guessing it's neither one. Is that a perfect derivative? If it is, then there is an implicit solution. And that's what we know it is, okay? So here is the definition we use basically to determine what an exact equation is. Now, I've got boxes in the way everywhere. Here, I think I've avoided them right here. Okay, kinda anyway. Yeah. All right. A differential equation, m of xy dx plus n of xy dy, is an exact differential in a region R of the xy plane if it corresponds to the differential of some function f of xy defined on that region R, and the first order differential equation of this form is said to be an exact equation if this expression on the left-hand side is an exact differential. That almost sounds like they're talking in circles, doesn't it? Well, yeah, they sort of are, okay? But this is what we mean by an exact differential equation. If that can be broken down into a single function f, so that m of xy is the partial of f with respect to x, and the n of xy is the partial of that same f with respect to y. Okay. Now, there's too many things here. Okay, go away. Okay. Here's an example. X squared y cubed dx plus y cubed x squared dy equals 0. Is that an exact equation? It certainly has a certain type of symmetry seeming to it, but let's see. They say it is because the left-hand side over here is exactly the derivative of 1/3 x cubed y cubed. Okay? Because if you take the partial of this thing with respect to x, that's going to be 3 times 1/3, which is 1, x squared y cubed. Look at that. And if you take the partial of this thing with respect to y, that's going to be 3 times 1/3, which is 1, x cubed y squared. There that is. So sure enough, that is an exact differential. So you could solve that differential equation. We don't know how yet, but you could. Okay? You can. We will be able to in the future. Now, can you always look at them and tell like that? Not really. I can't anyway. Maybe you can. Maybe you're far better than I am at it. Okay? Notice that if you make those identifications, your m of xy to be that, the n of xy to be this, that's pretty simple. Now, here's just a note. What happens if we take the partial of m, not with respect to x, but with respect to y? The partial of m with respect to y. So this thing here, take the partial with respect to y. That would be 3 x squared y squared. Okay? 3x squared y squared. Well, let's also take the partial of your n, but this time take it with respect to x. That would be 3 x squared y squared. Same thing. Okay? And we know this is an exact differential. We just determined that. We just noted these two partials are equal. This next theorem says that's no coincidence. That will be the case no matter what. So basically this gives you the test to see if you have an exact differential equation. Here's the theorem. This is also your test. Let m of xy and n of xy be continuous. Now they have to be continuous in some region R. Okay? Now what does that mean? No places where they take off and go to infinity there. No places where you have piecewise defined functions that don't connect. They've got to be continuous, and they have to have continuous first partial derivatives within this rectangular region R. The R is going to be something between A and B for X, between C and D for Y. Then a necessary and sufficient condition that this be an exact differential, m of xy dx plus n of xy dy is an exact differential. Here's all you have to show. Is the partial of m with respect to y equal to partial of n with respect to x? So you do the partial of this one with respect to the other variable, do the partial of this one with respect to its other variable, evaluate them, see what they are. If they are the same, bingo. No, you can't say that in Alabama. It works. You can do what we're going to do later. We haven't talked about how we solve these, but that allows you to proceed to solve. Okay. Now let's move to they're going to spend some time on the proof of necessity here. Now, this again is hitting something that Melissa probably hasn't had. I don't know if Corbin had it or not, or if Cole had it or not, if you've had Cal 3. But when you get to Cal 3, or when you get to the point in Cal 3 where you're doing this, okay, you'll find out if a function f behaves well, meaning continuous, the derivatives exist, all like that, that your mixed partials have to be the same. Because remember, with a regular derivative, dy dx, you take a second derivative, it's d2y dx squared. That's all you got, because you only got one independent variable, one dependent variable. But when you have two independent variables, that means you could take the first partial of f with either respect to x or y. We've just seen that, okay? That you didn't have before. There's only one independent variable. But then when you go to take a second derivative of f, you could take it the second time with respect to x again. That's 2 d2f dx squared. Well, yeah, that's a lot like taking a second derivative. Or d2f dy squared. Again, like taking a second derivative. And those are second derivatives. But you could have taken the first time the partial of f with respect to x, and then the next time taken the partial of that derivative with respect to y. And that's called a mixed partial. Partial of f, the second partial of f, first time with respect to x, the second time with respect to y. And here's something about smooth, well-behaved functions. Well, I even want to say smooth. Continuous, well-behaved functions. That the mixed partials are equal. It doesn't matter whether you take the partial of f, second partial of f, first with respect to x and then with y, or first with respect to y or then with x. If it's a well-behaved function, it won't matter. That's why, remember, this thing represents the partial of f with respect to x. This thing represents the partial with respect to y. So if you reverse the order and take the partial of this with respect to y, you're taking the mixed partial here. Second partial of f with respect to, first with respect to x, then with respect to y. And this one would then be taking the partial of this with respect to x, would be first taken with respect to y, then with respect to x. These are your mixed partials then, and as long as the functions are smooth and continuous in that region, those mixed partials should be the same. And that is basically your proof of necessity, with a lot of blah, 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 hand waving. Now, so I don't want to go any more to that. Melissa, you'll get to this in Cal 3. Promise you. Okay? Well, I hope you will anyway. All right. Now, before we launch into our method of solution, because I've been through this before, and it can be a tad tedious, it's not too bad. Let's have a pause. I need a bladder break, and we got about an hour to go. I'm not sure I'll make it then. So this is a good place to stop, or at least pause. So I'm going to pause the recording right now, and let's take a quick break. If you need to get up and go, go. Otherwise, stretch, do whatever. Wake up. No, I wouldn't say that. Let's get back in just a couple of minutes, okay? I'll leave Zoom on, but Now, basically what we've already talked about is almost enough to justify how we're going to proceed with this method of solution, okay? Now, what we've already said, you're given an equation of a differential form, m of xy dx plus n of xy dy. Two completely different, weird-looking functions of x and y here. They don't have to look at all similar. But here's a requirement, that m of xy dx plus n of xy dy has to equal 0. Okay, if it doesn't equal 0, try some other method, because this one will not work. That is a key feature, that it has to equal 0. This differential form has to equal 0. So, first thing you do, make sure that your test works. What we just talked about. Take the partial of m with respect to not x, but with respect to y. Okay? Then take the partial of n with respect to not y, but x. See if they're the same. If that works, if that equality holds, then proceed. Okay. Now here's it feels like we're backtracking, and in fact we sort of are. Remember what we said this was? This was, okay, time out. Let me start over. Here's where I like to begin. I like to begin. Now, you see, this represents some function, that represents some function. Okay? Now, this entire thing is supposed to represent df basically your df, okay? Not partial. That is your total derivative. I couldn't think of the word. The total derivative of f, okay? And that has to equal 0, which means that f is some constant function. So f of xy, and I sort of like to write that down at the very beginning, f of xy is equal to a constant. We're going to be coming back to that. It has to be that way because this is the total derivative of that function f. And that's equal to 0. So the function f of xy is a constant. Keep that in mind. Now, but it's still a function of x and y. Now, this thing here then has to be the partial of f with respect to x. Remember, when we do a total derivative, that's what this stands for. So write it down. Okay? Now, this is in derivative form, even though it is partial derivative form. Let's just kind of treat it. Now, this is where it gets a little flaky here. Kind of treat it as if it's a normal derivative. In other words, a df dx. You know it's not because f has two variables, but we're treating the y as if it's a constant. So with the y treated as a constant, even in this function m, you treat it as a constant, then move your dx over here and integrate. Okay, write that as a derivative as a normal differential form. df is equal to m of xy dy. I mean dx, okay? Write this on this side. Understanding the y at that point is being treated as a constant, okay? So, integrate that thing, okay? Take the integral of this side, that's going to be your f of xy, with y being a constant. Integrate this side, only with respect to x now, because there's a dx out here. Treat the y's as if they're a constant, okay? But, when you do that integral, remember, it's an indefinite integral because you could have a plus c. But guess what? Your y is treated as a constant, so any function of y is also a constant. So you don't say plus c, you say plus g of y. Now there's nothing magical about g. It means some function of y. Because you treated y as a constant here, that means you could have some function of y here that when you took its derivative, it's going to be 0. Derivative with respect to x, that would still be 0 because it's a function of y and y alone. Okay, so now we've got one expression for your f of xy. If you can do this integration, that gives you functions of x and y in here. Out here you have a function of y alone. Okay, so what you were calling your arbitrary function g of y is now your constant of integration because you are keeping y as a constant. Now, what we do is now turn around and differentiate that. That's your f of xy with respect to y, partial derivative, keeping x as a constant. Okay? So take the partial of this thing you just got here. This is some function of x and y. This is a function of y alone. Take the partial of that with respect to y. Now this makes it look really hairy. Once you actually put values in here, it's not quite as bad. And this just gives you a y prime because that's a total derivative of this. And set that equal to whatever your n of xy was. Right here. Set that equal to that because it has to be. Now, they make this seem really difficult. It's really much easier when you really have functions in here. They say that gives you this is equal to n minus this. Now this is making this more difficult than it needs to be, but it's doable. This is a function of x and y. This is a function of x and y. And this is a function of y alone. Okay? So you're hoping that somehow your x's take care of themselves here. And when you do that, then your answer for that, when you differentiate this and get what g is, plug it back in up here, and you've got your f of xy. But remember that f of xy is equal to a constant. That's what I said at the very beginning. Take that function you just determined and set it equal to a constant. That is your solution. F of xy is not your solution. F of xy is equal to some constant. That is your solution. Now, they say some observations are in order. Some clarity might be in order, okay? We'll get to it when we actually put functions in there. First, it's important to realize that the expression n of xy minus the partial, this thing right here, partial with respect to y of your m of xy dy, blah, 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 has to be independent of x. Otherwise, there's no, yeah. So when you do this, you'll see the x's fall out, okay? If they don't, this isn't, something's not worked right, okay? It has to be, okay? Now, and they go through a lot of mess here. And if you were to take the partial of that with respect to x, since it has no x dependence, we just said it depends on y alone, this had better be 0. And when you do that, the partial of n with respect to x, we've already done that, minus this thing. Well, this thing is the partial of m with respect to y, because this is a derivative of an integral with respect to the same variable, so that gives you this. Well, there's what you had to begin with. The partial of n with respect to x has to equal the partial of n with respect to y. Now, that's one observation, which if you've done it right, you won't have to fiddle with that. Secondly, you could just as well have started up here where we started with this and said that partial of f with respect to x is equal to m of x. You could have started to say the partial of n with respect to y is the partial of f with respect to y is n of xy. So if one of these look like it's going to be easier to integrate, use it. Don't go for the hard one. If things get really awful looking when you're doing this step here, go back and try it the other way, okay? There's no magic, nothing that says one is any better than the other, so do the one that's easier. But when you do that way, then if you start with that, then you integrate with respect to y, your constant of integration has to be a function of x alone, and they call that h of x. You can call it anything you want to. And then your solution at the end is going to be just like this was your g prime. Your h prime is going to be m of xy. And don't worry. Don't try to memorize these formulas. Just do the work, okay? The steps minus this. And it says in either case, here's what it says, none of these formulas should be memorized. That's not how you do these. You do the procedure, okay? So let's do the procedure. Here's the first example. I think you see all that blah, blah, blah. It was sort of necessary to get the theory down, to get that everything's legitimate. Let's just do it, okay? So let me go to our white page. We still got 3 people here. That's good. I wish the others would show up, but they haven't yet. Let's go back to our whiteboard. Okay. I'm going to clear this one out of the way. Okay. Now, let me get example 1. Top of page 67. Okay. 2xy dx. Sometimes I like to put that in parentheses so I see that's my m. And then it's a plus x squared minus 1 dy is equal to 0. Now, that's our problem. It says solve that differential equation. And that's really in differential form. So this is truly, in many ways, a differential equation. Now, before we get going too far with this, I think we might need to note something. Remember, we're talking about some region, some domain, okay, that this is supposed to be identified on. Now, it seems like to me, just gut feeling here, that we probably don't want x equals 0. Because if x is equal to 0, this whole thing is equal to 0, right? And then you just have an x squared minus 1 dy is equal to 0. And with x equals 0, that means minus 1 dy is equal to 0. So that's just y is equal to a constant. And maybe that's okay. Maybe that's perfectly fine. That may be a, what do they call it? Going blank on my nomenclature here. It's sort of a special case solution. That's not what they call it. Okay. X equals 0, y is equal to a constant. Okay. Nor do we want y to be 0, I would think, because if y was 0, then that basically says that x squared minus 1 times dy has to equal 0. And that seems like that leads to some weirdness, possibly. Anyway, just watch out for those. Another, x looks like you might want to avoid plus or minus 1 as well. Okay? Maybe not totally, but these may form, these are just things that when you get used to looking at these, you say, ooh, what's going to happen if that happens? Okay? If that were to happen, that x is equal to plus or minus 1, then this whole term is 0. And then you would have 2xy dx is equal to 0. But x is either plus 1 or minus 1, so that would be 2y dx equals 0, or minus 2y dx. Yeah, dx is equal to 0. Well, you might want to look at those as special cases. We're not going to worry about that now. That's another thing, but usually not a bad idea to just think about, we have to watch out for x equals 0, y is equal 0, x equal plus 1, or x equal minus 1. We may need to pay attention to those. We may not. It may not be an issue. Okay. So what's our assumption? Our assumption is that we hope there's going to be some function of x and y that is a constant. Remember, that function has to be a constant. And here comes Ricky. Way to go, Ricky. Let's get Ricky here. All right. No, I just marked. Ricky's the top of my class. I mean, the first name in the class in my linear algebra class. And I just marked Billy here because, so I'm going to do a little circle there. Okay, sorry about that. Okay, welcome, Ricky. Let me just tell you where we are. We finished section 2.3 linear differential equations, first order differential equations, with that problem on the error function. That was sort of a pain in the neck, but not too bad. And we've started on talking about exact differential equations. So we've already talked the theory of it. You're here for the first practical application. This is not necessarily how every exact differential equation will look. If it doesn't look this way, you need to make it look this way. You write it in differential form, okay? And notice this is a function of both x's and y's. This is a function technically of x's and y, though this one happens to be only a function of x. It's okay. Our assumption there is that there's some function of x and y, a constant function of x and y, such that its partial with respect to x is going to be this, and its partial with respect to y is going to be that. Okay. And that's where we begin our solution process. So let's just do, oh wait, no, time, no. We have to first see if this even qualifies as an exact differential. Remember, there's certain things that have to happen in all these. What has to happen here is the partial, now this function we call m of xy. This one we call n of xy, even though there's no y in it, we'll still call it n of xy. The first thing we do, and since this is supposed to be the partial of f with respect to x, and this is supposed to be the partial of f with respect to y, we're trying to find what that f is, we have to see if this is an exact. And here's the test. We do the partial, and Ricky, you have had Cal 3, right? Wasn't that last summer?
Uh-huh.
Okay, good. So you've taken partials before. The partial of this thing right here, remember we're calling that our m. And we're taking the partial of this with respect to the other variable. This is respect to y. Okay? And we're going to take the partial of this one. This is called our n. I had an old guy in my class. I mean, he was older than me, 78 years old, last summer, and he came back in the fall. He called these curly D's. Have you ever heard that term? The partial derivative, he called them curly D's. And I thought that was a pretty good way to name them. I always have to call them partial derivative. You call it curly dn, yeah. So rather than dy dx, he would call it curly dy dx. Okay. This is the partial. You take the partial of this now with respect to the other variable, x. So let's do this. Partial of m, this is your m, with respect to y. Treat the x as if it's a constant, and that would just simply be 2 times that constant x, right? Because this is linear in y. Derivative with respect to y would be 1. So the coefficient here for that would be 2x. So that's 2x. Let's take the partial of this n right here with respect to x, the other variable here. Well, partial of that with respect to x is again 2x. Guess what, team? Those are the equal. If those are equal, that means we can proceed. So let's do it. Now, that was our test. We're not going to use that test again, so we can get rid of it. And I'm afraid I'll need the room. Well, let's leave it there. If I need it, I'll come back and erase that later. All right. So what's our procedure? Well, we go back to our original assumption. If there is a function f of xy that's a constant, that this is the perfect derivative for, that means this thing right here is the partial of f with respect to x. Okay? So let's write that down. The partial, and this is what we're looking. We're looking for the f. F is not going to be your solution, but it helps you get your solution. The partial of f with respect to x D's are hard to write. Curly D's are pretty hard too. That this is supposed to be your m. That thing right there, 2xy. since we're going to treat the y's as a constant, just pretend it's just a constant, 17/3 or whatever you want to pretend. It's not a y, it's a constant, okay? Okay? Then this you can treat like this is a regular derivative. So write that in differential form and do df. This is a little bit of a shaky deal here, but it's legal in most states, is equal to, now I'm going to leave the 2 inside because I'm sort of psychic or psychotic or something like that, because I know I'm going to be using it. 2xy, oh wait a minute, I shouldn't have put the integral sign there yet, but forgive me for that. I should have just written in differential form. Okay, move my dx over here. Okay, then the next step is integrate both sides. Okay, now integrating a perfect derivative, that gives you your f. You might say, are we through? No, not yet, because this is a form of it. Now remember, we're only integrating with respect to x. We're treating y as if it's a constant. Okay. So, with respect to x, this would be, anyone want to hazard a guess? Antiderivative of 2xy if y is a constant? Basically, maybe what I should have done is pull the y outside so it's not even in our way. We're treating it as a constant, so get rid of it. I mean, don't get rid of it. Pull it outside the integral. And what's the integral of 2x? dx, antiderivative of 2x. Come on, you can do it. Come on. X squared, right? So this will just be x squared y. But this is an indefinite integral, remember, so we need a constant of integration. But remember, we're treating the y as if it's a constant. So I think their function there would be plus some function of y alone. No x can be in this function of y alone, because we were treating y's as if they're constant. So our constant of integration here is a function of y. All right. Right? Well, if we knew what g was, we knew our answer right here. But we don't know what g is. Okay, so let's see what we can do. Well, we also know that the partial of f with respect to y has got to be this n right here. So let's do that. Let's take the partial of this with respect to y, which is also taking the partial of this with respect to y. Wait, why did I put an integral sign there? Goodness gracious, where's my brain? Okay. Uh-oh. Eraser's not working. I don't know why it does this at some point. So this is not there, folks. I can't erase it. Okay. We're taking the partial of this with respect to y. And we're taking the partial of this with respect to y, but this is only dependent on y, so this becomes g prime. We don't know what g is. We don't know what g prime is. Okay? That's beside the point. Okay. Now, if I could erase that messy looking stuff there, which for some reason it won't let me do it, and I don't know why. It's stuck on the draw and won't give me anything but the draw. Okay. So let's do what we just said. I think I'll come over here. So, yuck. It's drawing now without me pressing the button down. The partial of f with respect to y is equal to, now we can do this partial derivative here. The partial of this with respect to y, because you treat the x squared, x as if it's a constant, so x squared is a constant. So you only take them with respect to y. Well, y is to the first power. That's just going to be x squared. Okay? Plus g prime of y. That's derivative of g with respect to y. Okay. Now that's our partial of f with respect to y, with this being our f, thing we had down here. Okay? Now, this is supposed to be this. So let's put that in its place. Remember, partial of f with respect to y was your coefficient of your dy. So let's put that down. This is x squared minus 1 is equal to x squared. See, you don't have to worry about subtracting integrals or anything like this. This is g prime of y. Because guess what happens now? We need to solve this for y, but guess what? You subtract off your x squareds, they go out of there. So now you have dy, I'm going to write it this way, dg dy, that's a d now, not a partial, even though it looks sort of curly. It's not. It's equal to minus 1. That's all, folks. So write that in differential form and integrate both sides. And you have g, it's supposed to be a g, of y, remember it's only a function of y, is equal to, hopefully you see that as minus y. Now, at this point, you might be tempted to put in a plus c. Resist temptations. Leave that as your g of y. Let me make sure that we've gotten to the same place they have. Okay? Yeah. Don't do a constant of integration. What we do with this now is go back to this, where is it? This statement here. Let's see, where is it? I've messed up so much. Okay, yeah, this statement, right? No? Yeah, before I took derivatives, I'm doing too many steps at once. When we had f is equal to x squared y plus what g of y. Before we took the partial, and derivative. Before we did that, go back to this step. So here's our f. That's f of x and y. It's equal to, and before this got all messed up here, that was just an x squared y plus g. Before we took the derivative, that was just a g there. Well, your g is now minus y. Minus y. Now, that's not your answer. Your answer is set that equal to your, there's your constant. That's why you didn't need to put constants of integration here or there or anywhere else. You're going to do it here from this statement right here. There's your constant of integration. This is your solution. Now, can we write that as an explicit solution of y? Yes, we can. We could factor a y out of both terms. And that gives us y times x squared minus 1 is equal to c. And then you could say y, this is ugly, is equal to c over x squared minus 1. Now, if you chose to write it like that, you see obviously now x can't be plus or minus 1 because y would be undefined then. Our other things up here about x equals 0 and y is equal to 0, I think that's going to be fine. When x equals 0, your y is just minus c. When y is equal to 0, the x is equal to, let's see, I don't know, I'm not sure why it can be 0, can it? Okay. Well, don't have to sweat that, I don't think. Okay. Now, those are our two ways of giving the answer. Here's one answer that's perfectly legitimate. If I could get my cursor. That's a good answer there. X squared y minus y is equal to c. Just factoring out the y, you could write that as y times x squared minus 1 is equal to c. That's a perfectly fine answer. Or dividing both sides by this, and that gives you y is equal to c over x squared minus 1. Okay? So, with that in mind, let's go back to our book. Okay. And here's what they got. Hence, f of xy is equal to x squared y minus y. Yes, we got that. Well, we got that. That's what your f is. But your solution is not that. Your solution is this thing equal to a constant. There's your constant of integration. All those integrations all piled into that one. And you could also factor that out. They didn't show it. And that would be y is equal to c over x squared minus 1 is defined on any interval not containing either x equal 1 or minus 1 or x equal 1. So it could be over here anything x is less than 1, less than minus 1, perfectly fine. Between minus 1 and 1, just not including. That's a good interval. Or over here to the right of 1. All those are legitimate intervals. If you had an initial condition, you're going to be in one of those places, and that's the only solution then you have. So these are three possible places where you could have solutions, but it can't be, your solution is only going to be one of them. Now, let's see what the notes say. Okay. Go back here. Yeah. 4 people here, that's what we got. All right, note, the solution in differential equation is not this thing. Even though you work so hard to get it, that's not your solution. Rather, it's whatever you found this thing to be, this, equal to a constant. That's your solution, okay? And don't write it as f of xy equals z. Write it as x squared minus y, x squared y minus y equals c. If a constant is used in the integration, okay. If you did put a constant when you did do the integration of this f g prime, then your solution would be f of xy equals 0. I don't even know why they put that in there. Your solution is this thing's equal to a constant c. Okay. So let's, whoa, goodness gracious, where did that go? Oh, I know what happened. I hit a key. I hadn't been moving my cursor. I had just been moving the thing. So when I hit the arrow key, it went back to the cursor. So let me catch it. Okay, here's where we were. Okay, that's where we just were. So now we're going to move on to example 2. I think we have time for it. We go to 10:45. Let's see if we can get this one done. All right. This looks maybe just a tad more complicated, so we may not finish it, but let's at least get started. Let's go to our whiteboard and start working on this one. Let's clear this. Does anyone need this one here any longer? No? Okay. So here's example 2. Yeah, right. Okay. Open parentheses. E to the 2y minus y cosine xy and they don't put it in parentheses. I'm real tempted to, but since they don't, I won't either. Cosine xy, close your parentheses, and this is that's your m of xy dx, and the pen is sort of skipping some, okay, and then you have a plus sign, another parentheses, which is usually a bad sign, 2x e to the 2y minus x cosine of xy. Thought it had to be that. Okay. Plus 2y. Why not? Throw something else in there. Okay. And that's times your dy in differential form. And that's equal to 0, which it's got to be, okay? Now, the book doesn't usually do this, but I just tend to feel like it's a good thing to do. Our supposed solution is this. F of xy, if there is some function f of xy that fits that bill there, then this f of xy has got to be a constant because its derivative is 0. Okay, so that's going to be our solution. We'll come back to that later. Okay. Before we proceed, before we do anything with that f, let's check and see if indeed this even has a chance of making. What's our test? Now, Ricky came in probably after we did this. What's our test? The partial of this thing, I don't want to write it all down, so I'm just going to call it m, with respect to the other variable y. Let's see what that is. Now that's taking the, okay, time out, just a moment, time out. Do any of you think we might be able to solve this differential equation by separation of variables? If you so, raise your hand. I don't see any hands. Do any of you think there is an outside chance this may be a linear equation, either in x or y? If so, raise your hand. I don't see any hands. There is no other way we've got so far for solving this differential equation except hope and pray it is exact. Okay? So let's see if it is. Here's the first test. Take the partial of this thing here with respect to y, the other variable from here. Well, what is the partial of e to the 2y? Anybody? And we're running rapidly out of time, so that's 2 times e to the 2y, right? Chain rule. and that was only a function of y, so that's perfectly legitimate, minus, SpaghettiOs. We have a product rule here, okay? I don't know how you like to do the product rule, but let's just do the first. That's just going to be a y times the derivative of the second. Well, derivative of a cosine is a minus sign, so that's going to make a minus here. It's going to have a sign here if I could write of xy. Now, they're only taken with respect to y, so we're treating x as a constant. So its chain rule tells us we have an x out here too. I sort of wish I'd have left my space in front of the y, not there. Okay. Now, remember, there was originally a minus sign there. So there's still that minus sign there. Watch out for minus signs. The only purpose they have in their whole existence is to trip you up. So be very wary of them. That has to have a minus. So it's minus the second, that's cosine xy, times the derivative of the first. Well, the derivative of y with respect to y is 1. So that's just minus a cosine. I can't write. The pen is not cooperating. Cosine xy. That's an O in the middle of that. All right. There's your partial of m with respect to y. Now we do the same thing over here, but take the partial, this is our test, of n with respect to x, the other variable. That really is a curly d. Okay, and what's that? The partial of this one with respect to x. Well, you might almost say we have a product rule, but we don't, because we're treating the y's as a constant. So this is x to the first power with a big coefficient in front of it, 2e to the 2y. Derivative of that is just 2e to the 2y. That's the partial of that first term with respect to x alone. Now the second term is a product rule, okay? So I'm going to put down the minus here, and the first is the x, because we're taking with respect to x, and then we're going to have derivative of a cosine, which again is a minus sign, so that makes that minus become a plus, sine of xy, and then we take chain rule, derivative of the argument there, with respect to x, and that would give us a y. Okay. Minus, because that minus is still there, the second times the derivative of the first. With respect to x, that's just going to be a minus cosine xy. Okay, and then we have one more term here, but we're taking the partial with respect to x. 2 is a constant. We treat y as if it's a constant. That's a 0. So, what do we have here? 2e to the 2y, both of them, plus xy sine xy in both of them, and minus cosine xy in both of them. They're identically the same. That means we can proceed. All right. Okay. 9 minutes. Okay. Now, I wish I had my eraser, because I definitely want to erase that, because we don't need it. We don't have room for it, but I can't get rid of it. So let's proceed. Now, the question is, which one of these do we go with? And I really don't think it matters too much. Let me look ahead in the book and see if it matters. they start with the second one, and I don't know, they make it sound like it's just random. They say for variety, they're going to do that. Do you want to do that? Which one do you want to start with? Frankly, it seems like to me this one has two terms. That may be easier to work with. I may be totally wrong. Okay? But let's go with this one because we're short of time. And then we'll compare it with the book. Okay, our assumption is that there is some function that's a constant function that when you take the total derivative of it, you'll get this, which means the partial of this thing right here with respect to x must be that. So there's our first assumption. The partial with respect to partial of f with respect to x needs to be this thing. E to the 2y minus y cosine of xy. This is so tedious. Okay. All right. Now what we're going to do is pretend y's are constants. Your constants are any constants is up to 2 stuck in there are constants. So we're just going to move and make this a dx over here. And then we're going to integrate both sides of that. With respect to x. Okay? Now this would then give us an f, which is a function of x and y, but that's fine. F is equal to, now, with respect to x, the antiderivative of this, remember, y is a constant, so this whole thing's a constant. This would just be an x, the antiderivative of that would be x, e to the 2y. E to the 2y is just like a constant. Take it outside the integral. Oh, now my pen's not stopping writing, so it's just keeping writing. Okay, it finally stopped. That's the e to the 2y. Sorry, the pen just decided to keep writing. Okay, over here, integrating this with respect to x. Again, the y is a constant, so let's pull that out. Minus y, and then we're going to have the integral of cosine xy, only the y is a constant. So pretend that's a yx, but I'm going to leave it as a xy, where y is just a constant, dx. Now, we're not quite through, so I'm not going to put my g there yet. So this f is equal to, this is fine. This is x e to the 2y minus y. Now, you tell me what the antiderivative of cosine yx is. Remember, y is a constant. Well, the antiderivative of cosine, say again? That's going to be sine, a positive sign. Okay, so we don't change that. That's going to be a sine of xy. But now remember the the y is a constant here. So then we're going to be dividing by that constant because this is a derivative. And dividing by that constant is going to wipe out that y. Oh my goodness, look at that. Now we put in our constant of integration, which is your g of y. Because remember, we're only taking with respect to x, so y could be, we're treating y as a constant, so it's going to be a g of y. All right. Now, I think we chose the better route here. Okay, that's looking better than the other. Now, this is our g, f, if we only knew what g was. Well, how do we get g? We take the partial of f with respect to y. We took the partial of f with respect to, we said, here. So let's take the partial of f with respect to y. Okay. Now let's do it. Again, treat x as if it's a constant. And I'm doing this fast. That would be 2x e to the 2y. Does everybody agree with me? You better say yes. No, think about it. Okay, you really mean it. Okay, that is your partial of f with respect to y. And in this term, remember these y's went away, so that's going to be the derivative of sine is cosine, so that's going to be a minus, and it's with respect to y, so x is going to be a coefficient here, chain rule, cosine of xy. And the derivative of this with respect to y is just g prime. Whoa, that went way too far over. Now, but this thing here, the partial of f with respect to y, should be this thing up here. So let's just set that equal. That is your partial of f with respect to y, is this thing right up here. You're in. Okay? So this should be, whoops, it started writing again, well, I didn't tell it to, 2x e to the 2y minus x cosine xy supposed to be an x there. Okay, plus 2y. Now that's supposed to be equal, but let's look and see how equal that is. These two are exactly the same. You could subtract those off. These two are exactly the same. You could add those off, okay? And that leaves you your g prime is equal to 2y. I think most of you could probably guess what g is. G of y is equal to, please tell me, y squared, right? You could integrate it if you wanted to. You could say this is dg dy is equal to 2y. Then write that in differential form. dg is equal to 2y dy. Integrate both sides. G is equal to y squared. Now, we've got our g. Now we know what f is. So our f is this thing right here. X e to the 2y minus sine of xy plus g was y squared and then stop the horses, set that equal to c. Now I shouldn't have written that all in one line, but that's it. Here is your solution, right here. If I could draw a box, okay, that's your solution. Let's see how the book did. Okay, we're out of time. Let's just quickly go back to the book and see what they got. Now they show all the steps here, I think. They first checked and saw that the partial of m with respect to y is equal to the partial of n with respect to x. That works. They did that. They chose the other route. So theirs is going to be, I think, messier. Maybe not much messier. But let's see what their final answer was. x e to the 2y minus sine xy plus y squared. They put plus c equals 0. I put equals c. It doesn't matter which way you put it. Why they changed it, I'm not. Oh, probably because they did it the other way. It doesn't matter how you do it. And I think that's exactly the answer we got. Let's start next time. Any questions on that before we leave it? We will start next time with example 3 on the top of the next page. Near the top of the next page, of this page right here. Any questions? Homework exercises here. Oh, goodness gracious. Let's scroll down so you can see them. Here we go, getting close. Okay, any of the odds 1 through 19 that have answers in the back of the book. Try any of those. I can't show them all at once. And have we done an initial value problem? I think that's coming up next. So hold off on the initial value problems. Any of the odds 1 through 19. Any questions? Was that a question?
No, sir.
No. Okay, great deal. Okay, well then have a good weekend. And of course, working on differential equations will guarantee it'll be a good weekend, right? Say yes. Okay. Have a good one.
Thank you.
Okay. I'm going to stop the sharing. I don't like to share. And we'll end the meeting if there's no more questions. Take care. Be safe. All right. I'm going to end the recording too.